Thank you, Alan. I'm going to give you an update on our work towards sub-10 nanometer diameter indium gallium arsenide vertical nanowire MOSFETs and TFETs, and I'm going to come over here since that podium is on the way. And so let me start by acknowledging the work, of course, of my students and collaborators, and also the funding of NSF through the E3S Center, LAM Research, and some other institutions that have funded our work for quite some time. So let me see. I guess maybe it doesn't reach all the way over there. The other button, yes. So this is about scaling electronics to its limit. And if you look at the evolution of structural design of logic transistors, we are getting close to the end of the road. We are quite advanced from planar MOSFETs, to FinFETs, which is the current state of the art, to eventually the ultimate scalable transistor architecture, which is going to be the vertical nanowire gate all-around transistor. This is a design that has the potential of scaling to the smallest dimensions and therefore yielding the highest transistor densities that are possible. Now, this is a very compelling transistor structure because it has a very unique feature that no other architecture has, which is that the design of the critical dimensions of the device, which are the gate length, the contact length, and the spacer length, does not cost you any footprint. And as a result, you can optimize the transistor in ways that that is not possible in any other transistor structure. By putting also the transistor on the edge or on the tip, it really occupies an extremely small footprint and is amenable to a very high density of integration. So this is a very interesting transistor structure with tremendous potential. Now, there has been quite a bit of work in the area of vertical nanowire transistors. I'm going to confine my discussion today on 3/5s and in particular indium gallium arsenide, because among the 3/5s is the material with the greatest potential for future N-channel transistors. There has been a lot of work in preparing nanowires and eventually transistors based on bottom-up techniques through the growth of the nanowire in the first place and then the fabrication of a transistor on it. And so we've seen the vapor solid liquid technique that has yielded great results. This is the work that is done at Lund University, as we'll probably hear on the next talk, using a gold seed. But there has also been a very nice work without the need for a gold seed, using selective area epitaxy on a templated silicon substrate, as you can see here. You can see here the work of IBM in Zurich, giving rise to beautiful forests of vertical nanowires of indium arsenide on silicon. And because of the very small size of the interface, you can get a very coherent interface between the indium arsenide and the silicon in spite of the very large lattice mismatch that exists. So these are bottom-up techniques to prepare these nanowires. Now, we don't have bottom-up growth capabilities like this, so we have been working for some time on top-down techniques. We start from a heterostructure that looks roughly like this. So fairly simple. In the indium gallium arsenide system, you have an N+ indium gallium arsenide layer, a thin undoped layer, and then a heavily doped layer on top. And essentially, when you cut a wire through this, one of these sides will be the source, the other the drain, and this is going to be the channel length of the transistor, all taking place in the vertical direction. And once you can make this nanowire, you can wrap a gate around it, expose the top tip, put the contact on top, put a contact on the side, and there you have it. You have a working transistor. So this top-down approach is very flexible and manufacturable because I have a great deal of freedom to design these heterostructures, since I will then form a wire on them. And it's a very attractive approach. But of course, it relies on having very advanced etching capabilities. And that is what has taken quite of our attention for the last few years. And our way to etch these nanowires is essentially a two-step process. We first rely on reactive ion etching using this particular chemistry that we have developed for some time under very precise conditions to start with a nanopillar of indium gallium arsenide in this particular picture that already has a very high aspect ratio and a rather thin diameter. So you see in this case 28 nanometers, 240 nanometers tall, a beautiful, almost perfectly vertical sidewalls. But this is not quite enough. You want to go beyond this by trimming these nanowire into much smaller dimensions through a technique that is known as digital etch. It's a technique in which you essentially are chemically etching the walls of the nanowire, but you do this in a very precise way by splitting the two elemental steps in chemical etching and doing them separately. So in the chemical etching of semiconductors, you oxidize the semiconductor surface, and then you dissolve the oxide. And typically, this is all happening at the same time, and it's very difficult to control. But if you do these two steps separately, then each one of them is self-limiting, and as a result, you have a great deal of control over the etching rate. So in our case, we oxidize the semiconductor surface on a simple oxygen plasma reactor, and then we dissolve that oxide in diluted acids, such as sulfuric acid of HCl. When you do this separately, under the right conditions, you can attain an etching rate of 1 nanometer per cycle. And then by going around and repeating this a number of times, then you can, in a very controlled manner, trim the structure that you are fabricating. So you can see in the case of this nanopillar here, after 5 cycles of digital etch with a radial etch of 1 nanometer per cycle, so 2 nanometers in diameter, you end up with a diameter of 18 nanometers. But you can see how you do this while preserving a beautiful vertical sidewalls, smooth sidewalls, and a very nice aspect ratio. All right, so once you know how to form a nanopillar of this kind, then making a transistor is fairly straightforward. And here we have learned from the work of Lund University and also Hokkaido University. So essentially, this is the starting substrate. We use HSQ as a mask, shape the mask with electron beam lithography, reactive ion etch the nanopillar, trim it with digital etch, then deposit the gate stack, which in our case is ALD aluminum oxide, and then a tungsten gate, and do a first level of planarization to remove the gate, a second level of planarization to remove the gate oxide, and then we apply the top contact, and essentially we're done. And so I'm showing you here now the I-V characteristics of some of our most recently obtained transistors. These were published just earlier this year. And what you see here is a transistor, is a MOSFET in this case. Of course, everything that I'm showing you applies also to TFETs, and we also do TFETs, and I'll show you some characteristics later. But in this case, I'm showing you a MOSFET. This is a transistor with a diameter of 40 nanometers, so it's relatively large. But it's a single nanowire device, so it's just 1 nanopillar with the gate all around, and that makes a transistor. So that is why you see output characteristics here that have these fluctuations on them, because this transistor, this device being so small, it has very few traps, and as a result, trapping an electron here or there changes the conducting path in a way that is actually visible in the I-V characteristics. Nevertheless, it has nice output characteristics, pretty high transconductance, I'll show you in a moment. Very nice subthreshold characteristics. The linear subthreshold swing is 70 millivolts per decade. You know that the theoretical value at room temperature is 60 millivolts per decade, so this is quite impressive for a device fabricated like this. Very nice characteristics. Now, to put this in context, I'm showing you here all vertical nanowire transistors that we know of in the indium gallium arsenide system, and also in the silicon and germanium systems. I'm comparing them in terms of the transconductance, which is a key figure of merit that you need for just about any use of any transistor in any application that you can think of. So it's an extremely important figure of merit. So I'm going to show you transconductance as a function of the diameter of the nanowire. And this is an important metric because for these technologies to be relevant, this is where we need to go. We need to go, as I will show you later, to essentially 7 nanometer diameter or thereabouts for this technology to be relevant. And you can see that there's a huge gap as you approach that dimension. It gets extremely hard to make transistors with nanowires in that dimension. Now the red squares here, and the red star refers to indium gallium arsenide based devices. This is the latest result that I just showed you at 40 nanometers. The black dots refer to silicon or germanium or silicon germanium devices, which typically operate at higher voltages. So you can see, if you look as a whole, you can see that indium gallium arsenide in general is doing quite well in comparison with silicon and germanium. And so that is the good news. The bad news is that, well, the smallest transistor that has been demonstrated in the InGaAs system is somewhere around here, which is somewhere around 25 nanometers in diameter or so. And remember, we need to go down to 7. Silicon has gotten there somehow closer, but there is quite a gap. So this is the challenge. How do we get ourselves to make some transistors in this regime, which is where they are relevant? So, well, I've told you how to etch indium gallium arsenide nanopillars, so you would say, well, just crank the handle more times, do more cycles of digital etch. Sure, let's do it. Well, if you just do more cycles of digital etch, this is what you find. So here you have indium gallium arsenide nanopillars that started around 22 nanometers. And after 7 cycles of digital etch, we expected the resulting nanopillars to have 8 nanometers in diameter. You look at the resulting structures, and you can see that they're all destroyed. None of them are there. The yield was exactly 0. So clearly, just cranking the handle doesn't work. And the reason for this, as we thought about how to solve this problem, we thought was because we are using a water-based acid to dissolve the oxide that is forming the oxidation process, and that's the essence for etching to take place. And of course, water has a very high surface tension, and as you try to dry the water away and finish one cycle and then move on to the next cycle, there are enormous forces, mechanical forces that are applied on these tiny nanopillars that eventually get destroyed. And so we had the idea that if instead of using water-based acids, we use alcohol-based acids, then the problem perhaps could be solved. And that is because alcohols typically have a much lower surface tension than water, as you can see here, less than 1/3 in the case of methanol and IPA. And thankfully, you can actually buy sulfuric acid and HCl dissolved in some of these alcohols, so you actually are ready to go. So that's what we did. So actually, at the same time as we processed this sample, we processed an identical sample in which the only difference in the process was that here we used HCl in IPA, while in this sample we had used HCl, same concentration, 10%, in DI water. And you can see what a dramatic difference that makes. You can see here how the yield was 0, and here the yield was 97%. Essentially, all the nanowires actually reached that point, maintaining their structural integrity. You can see here, beautiful and formed 8 nanometer diameter nanowires. We went beyond, and if instead of HCl in IPA, we use sulfuric acid in methanol, we can actually reach a yield of 90% on 5.5 nanometer diameter nanowires. And that perhaps is due to the fact that the viscosity also matters, and that methanol has a viscosity that is about 1/4 that of IPA. And in fact, using sulfuric acid in methanol, we have obtained our hero nanopillar, which is here, which is an indium gallium arsenide nanopillar with a diameter of 5 nanometers, a height of 230 nanometers, with an aspect ratio in excess of 40. Now, you see me quoting the diameters up here because this is where the device is going to be made. And so this is where we pay attention. That is where we are trying to design these nanowires. So you can see that from the point of view of obtaining now sub-10 nanometer diameter nanopillars, we know now how to do it. Of course, the challenge now is to build a transistor around that. And that brings up new issues that are actually quite hard to solve. We are going to make a presentation at IDM where we're going to show very exciting transistors. But at this point, let me just show you this result, which is a 15 nanometer diameter indium gallium arsenide MOSFET with nice, relatively nice looking characteristics. Again, this is a single nanowire transistor, so it's a very little creature with very nice subthreshold characteristics, a linear subthreshold swing of 69 millivolts per decade, pretty nice transconductance, 460 microsiemens per micron. And if I put this back in the chart that I showed you earlier, you can see how we have now been able to cross below the most scaled silicon transistors and now enter into this regime in which this essentially is the most aggressively scaled vertical nanowire MOSFET of any kind that we know of that has been fabricated. But still, we need to go farther down here. But to show you results there, please come at IDM in about 2 months in San Francisco. Now, I've shown you here some results with MOSFETs, but of course making TFETs is essentially a parallel process, and we tend to actually process at the same time MOSFETs and TFETs. The starting structure is different, but the device fabrication is the same. So let me show you some relatively recent TFETs results. So here's the structure. In this case now the structures are a little bit more complicated. We have a P+ source down here, a tunneling heterostructure layer over here, and then the N+ drain at the top. Otherwise, the device structure is the same. And as I said, it's fabricated at the same time as the MOSFETs. These are some of the recent results that we have reported earlier this year. This is still a 40 nanometer diameter device. We're also in the process of scaling the diameters now. The channel length is 60 nanometers. And you can see here that thanks to the introduction of a final thermal process, we have been able to drastically improve the device characteristics. Again, this is a single nanowire transistor, so a very, very small creature, and hence the current fluctuations. You can see here the Esaki regime in the output characteristics when you go to into the negative regime, showing that indeed there is tunneling going on in here. And more interesting, more exciting is to look at the subthreshold characteristics of this device, where we show now very clear subthreshold behavior. Actually, over here you see the subthreshold swing as a function of the drain current. You see how over 2 orders of magnitude of current, we do see subthreshold swing that is below the thermal value. We see it both at 50 millivolts and at 300 millivolts. We see it on the upswing and on the downswing. Sometimes you get hysterical behavior that can confuse things, so that's not the issue here. So clearly we are now in a regime in which even devices with such large diameters are showing very nice steep subthreshold characteristics. And our hope is that with a significant scaling into much thinner diameters, we should be able to get much better characteristics. So with this, let me just show you some recent observation of random telegraph noise in some of these devices that indicate the presence of traps which could play a role in softening the otherwise sharp subthreshold characteristics. I know that Lund has done very beautiful work in this area recently, but we've been trying to also study this in our devices. And you can see in this tunnel FET, you can actually see an interesting feature there in the I-V characteristics. Depending on where you place yourself in these characteristics, and if you sit there and measure the current as a function of time, you will see some sort of white noise with an 1 over F noise with a 1 over F spectra. But if you sit in the right place, you would actually see random telegraph noise where you see an electron essentially being trapped and detrapped from one particular trap, changing the device characteristics. And that actually shows with a characteristic 1 over F square frequency behavior. This is important because there is quite a consensus emerging in the field that some of these extraneous traps, interface states, etc., are actually playing a role in softening the otherwise intrinsic sharp subthreshold characteristics. So we must understand this. So we need to know the nature of these traps, or where they are, so then we can have a chance to try to correct them. All right, with this, so I hope I have shown you that there has been tremendous improvement recently in indium gallium arsenide etching technology that has allowed us now to make indium gallium arsenide nanopillars with extremely small diameters and very high aspect ratio, beautiful sidewalls. I've shown you MOSFETs with record characteristics. I've shown you TFETs also with subthermal threshold behavior. And we have exciting results coming up at IEDM. So I invite you to come and check our paper. Thank you.
Okay, time for questions.
Professor Huang. Yeah.
Thank you very much for the very nice presentation, very nice results. Just a very simple question. Did you check out the temperature dependence or hopefully independence of the I-V characteristics of the tunnel FETs?
We have. The second generation that I just showed you here, we're actually in the process of studying these characteristics. And indeed, they show much weaker temperature dependence than our first generation devices that we demonstrated a couple of years ago, which did not show subthermal subthreshold behavior, clearly demonstrating that perhaps traps are really playing a role in softening the subthreshold behavior. And when you take care of them through appropriate passivation techniques, you can really improve things. Yeah,
okay. Yeah, very beautiful work. So one quick question. For the nanowire, for the 3.5 nanowire, you just try to control the diameter. Is it possible further better control the shape of the nanowire?
From just a plain cylinder to something more creative than a cylinder.
Yeah. Can you controllable?
Yeah, you can actually do that. I think Lund has done very nice work. And I think Lars-Erik might show some pictures. There are possibilities to control the shape, to shape it in some way by, for example, while you do digital etch, you could do masking certain regions. And also you could have different compositions along the length of a nanowire and then use some selective etching. And we're exploring some of those, particularly when you compare arsenides with antimonides, the etching characteristics are quite different. And so you can shape these nanowires to some extent. We have indications of that, but it's all very, very early observations.
Another quick question about the RTN of the TFET. So how many devices you can, how easily you can get the RTN?
The what?
How easily? I mean the RTN. You mean some devices cannot observe the RTN. Some devices maybe can observe the RTN. So I'm not sure. If very frequently you can get, or each of your nanowire TFET you can observe the RTN.
Oh, the subthreshold behavior, the subthermal behavior.
Random telegraph noise behavior, I mean. So
RTN, okay.
RTN, yeah.
We have not done enough of a detailed study of that, so I am not in a position to answer that. We don't know that. Yeah.
One last question here.
So when you decrease the diameter of the wires, aren't you worried about the current that you can get out of the device? And if it doesn't matter, then, and if it matters, how small can you go in terms of diameter?
Well, so from a technology point of view, I think maybe you can say we can get 5 nanometers. A different question is, can we make a transistor out of that? That's going to be quite challenging. In fact, I saw some pictures from my students recently of a 3 nanometer nanowire sitting there. It wasn't very pretty, but it was clearly there. So I don't think that's the point. Perhaps the point is, what is the diameter that makes sense from an application point of view? If you look at the design, the very detailed design work that has been done at IMEC for logic circuits based on vertical nanowire transistors, they find that 7 nanometer diameter nanopillars, or transistors based on 7 nanometer diameter nanopillars, are essentially the sweet spot for a technology for the 5 nanometer node. So that's our goal. Our goal is to be able to demonstrate 7 nanometer diameter working transistors, and to make them with very good characteristics, with very low parasitics. And we believe that's possible.
Just a quick question on the random telegraph noise. So you showed a jagged IV curve.
Yep.
And then you showed that the fluctuations were roughly on the 10 to 20 second time scale.
Yep.
So I presume that IV curve was indeed fluctuating on that 10 to 20 second time scale.
Yes.
Is that right?
If you trace it several times, you never quite get the exact same shape.
Never exactly the same. Okay.
All right. Thank you. Thank you much. Thank you.